All right, guys. So today we are looking at one-dimensional kinematics practice. This is just one-dimensional motion. And so number one says in 1986, the first flight around the globe without a single refueling was completed. The aircraft's average speed was 186 kilometers per hour. That's V bar, and I've got the wrong tool. So we've got V bar, average speed, is 186 kilometers per hour. And it landed at this speed and decelerated at negative 1.5 meters per second squared. So acceleration is negative 1.5 meters per second squared. And so we want to know how long did it take for the airplane to stop. We're looking for delta t. Well, we can look at our formula, and we know that our reference table says that acceleration is equal to delta v over delta t. And so if we know that this was the 186 kilometers per hour and it went to a complete stop, that's our total change. And we know that our acceleration is over here. We want to solve for t. So we know that delta t is equal to delta v divided by a. But we have to solve in terms of the same units. We've got hours and seconds and kilometers and meters. So the easiest way to do that is going to be to convert 186 kilometers per hour into meters per second. And so the easiest way to do that is going to be to let's go ahead and set up the whole problem in our dimensional analysis. So we know we need to have v over a, and so that is 186 kilometers in 1 hour. And we're going to divide that by acceleration. So let's put the acceleration 1.5 meters in 1 second squared. And let's look at this now. So we need to get meters in the top and the bottom, so we can cancel those out. So the way we get meters in the top, we're going to say that 1 kilometer on the bottom is 1,000 meters. That's going to cancel out our meters and our kilometers. And we're going to have then hours to seconds, so we need to make this 1 hour, and this is 3,600 seconds. And so that gets rid of 1 second, and then 2 seconds, and then hours, and all we're left with are seconds for our unit. We have acceleration with 2 sig figs. So our answer should be in 2 sig figs. This gives us 34.5 or 35 seconds. So that's number one. Question number two. In 1976, Gerald Hoagland drove a car 8 times 10 to the 2 kilometers in reverse. Fortunately for Hogan and motorists in general, the event took place on a special track. During this drive, Hoagland's average velocity was about negative 15 meters per second. Suppose Hoagland decides during this drive to go forward. He applies the brakes, stops, and then accelerates until he moves forward at the same speed that he had when he was moving backward. How long would the entire reversal process take if the average acceleration during this process is positive 2.5 meters per second squared? So A equals 2.5 meters per second squared. We know that A is equal to delta V over delta T, and we're looking for how much time. So delta T is equal to delta V over A. Our delta V, he starts at negative 15, and he wants to speed back up until he got to the same speed when he was moving backward. So delta V equals 15 meters per second plus, or sorry, minus the negative 15 meters per second. And so we have a change in velocity of 30 meters per second. And so we've got a velocity, we've got an acceleration, and we've got a time. So let's find it out. We've got 30 meters per second divided by 2.5 meters per second squared, which gives us 12 seconds. 2 sig figs because the acceleration is in 2 sig figs. Number 3. The Boeing 747 can carry more than 560 passengers. It has a maximum speed of about 9.7 times 10 to the 2 kilometers per hour. If a plane takes a certain After takeoff, if the plane takes a certain time to reach its maximum speed, suppose the plane has a constant acceleration with a magnitude of 4.8 meters per second squared. At what distance does the plane travel between the moment its speed is 50% of its maximum and the moment its maximum speed is attained? So delta x is what we're looking for. V max is 9.7 times 10 to the 2 kilometers per hour. What distance does the plane travel between the moment its speed is 50% of its maximum and the moment its maximum speed is attained? So let's divide this by 2. So delta V is equal to 9.70 times 10 to the 2 kilometers per hour divided by 2, which is while we're doing this, let's convert this to meters per second. So let's multiply it by 3,600 seconds. Multiply it by 1,000 meters. Divide by 3,600 seconds. So that gives us the velocity in meters per second, which is 1.35 times 10 to the 2 meters per second. So now we have to find our distance. We've got a velocity. We've got a V max. We've got our starting velocity. Our final velocity is going to be 2 times that, so that's 2.70 times 10 to the 2 meters per second. And if we've got a delta x and an a and 2 v's, we know that we need to use the formula that vf squared equals vi squared plus 2a delta x. And if we plug all those in and solve for delta x, we can say that delta x is equal to vf squared minus vi squared divided by 2a, and that means that delta x is equal to 5.64 times 10 to the 3rd meters. Our numbers are 3 sig figs, 2 sig figs, 3 sig figs, so we need 2 sig figs. So our answer is just 5.6 times 10 to the 3rd meters. Question number 4. I'm going to use a different color now. Brian Berg of Iowa built a house of cards 4.88 meters tall. Suppose he throws a ball from the ground level with a velocity of 9.98 meters straight up. What is the velocity of the ball as it first passes the top of the card house? So we're throwing a delta x equals 4.88 meters. We want a initial velocity of 9.98 meters per second. We want to know what final velocity is, and we know that acceleration is 9.8 meters per second squared. So this is a negative since we're slowing down as we go up, and so we find our VF. So VF squared is equal to VI squared plus 2a delta x. We can plug in our numbers and say that VF is equal to the square root of VI squared plus 2a delta x. And so we can plug this in and we get that VF is equal to the square root of 9.98 meters per second plus 2 times 9.8, that is a negative 9.8, times 4.88. And we can discover that our answer is, this has to be squared, and our answer becomes 1.99 meters per second. We have 4.88 is 3 sig figs. We have 9.98 is 3 sig figs, and so our answer should be in 3 sig figs. Question number 5. The tallest roller coaster in the world is the Desperado in Nevada. It has a lift height of 64 meters. If an archer shoots an arrow straight up and the arrow passes the top of the roller coaster 3 seconds after the arrow is shot, what is the initial speed of the arrow? Delta t is 3 seconds. Delta x is 64 meters. We know that acceleration is negative 9.8 meters per second squared because it's slowing down as it goes up, and we want to find out what the initial speed is. So we've got VI. Well, we actually have a formula that has this. We have a formula that says delta x equals VI times t plus 1/2 AT squared. We have t, we have x, we have a. We want to find VI. So let's solve for VI. We're solving for VI is going to be delta x minus 1/2 AT squared divided by t. And so we can plug that in. We've got 64 meters minus 1/2 of 9.8, negative 9.8, times our time, which is 3 seconds, 3.0 squared, divided by 3. And so we plug that in, and we discover that our answer is that VI is equal to 36 meters per second. We have 64 meters, that is 2 sig figs. We have 3.0 seconds, that is 2 sig figs. So our answer is 2 sig figs. Mary is going to have to wait for another video because I'm running out of time, and I will do this next video in just a little while. It will be linked at the bottom of this presentation.